Hi there, Ms. Heaton signing in to talk with you about two more colligative properties, freezing point depression and boiling point elevation. First, I want to quickly review what Ms. Ewald pointed out in her last screencast. She was talking about how when you add solute, the vapor pressure, the pressure of the solvent above the solution, is depressed. So there is less vapor above the solution than there is above the pure solvent. And that's because what happens when you add the solute is that the solvent gets tied up in dissolving or surrounding the solute, and so it's going to take even more energy to break those intermolecular forces and make the solvent evaporate and become a vapor. So there's less pressure, less of it as a gas. Well, the two properties we're about to talk about are related to that. First of all, we're going to look at the freezing point. Obviously, the freezing point is the temperature where particles become solids, so liquids turn to solids. You could also think of it as the melting point, because that's the opposite process. But basically what happens when something freezes is that the liquid particles, which have, quite a bit of energy, lose some of that energy and become organized solids. They organize themselves into a nice repeating structure. When you form a solution, though, the freezing point is depressed or lowered. And here's why. Because by adding the solute, it's going to get in the way of forming that pattern. These solute particles are going to try to get in the way, or going to happen to get in the way, or they're going to tie the solvent up, so it's going to be, tied up, dissolving the solute. So you're going to have to take away even more energy to make the solution freeze, which means it has to get to a lower temperature before it will freeze. Some applications of this freezing point depression are commonly seen in antifreeze. You put this in your car coolant so that when it gets really cold outside, the liquid inside your engine does not freeze. That would be bad because then your car would not run correctly. So adding something like propylene glycol or ethylene glycol, which are both, those are both solutes that you add, they can lower the freezing point of the liquid in your car. Also, you might look at a salt truck in the winter. Around here, we put salt on the roads so that we think of it as saying so that the ice will melt. Really what it does is it prevents the water that melts from refreezing back into ice. And, it can get too cold for the ice to work, for the salt to work on the ice. And that's because the freezing point hasn't been depressed enough. There's only so much salt you can add, and we'll do some calculations related to that in just a minute. And finally, some of my favorite, homemade ice cream. You put the solute, like rock salt, into the solvent, the ice, so that the ice will get even colder before it melts, which allows the milk to get colder and make some yummy ice cream. Here's the equation for our freezing point depression. It's delta T, the change in the freezing point, equals negative times the constant for the freezing point. This is going to depend on what solvent you're using. It's not dependent on the solute. That's true for all colligative properties. M stands for molality. Remember that calculation we did? There's a reason for it because it shows up in these calculations. And notice that we're using kilograms of solvent in our denominator. And finally, this value I, the Van Hoff factor. Let me give you an example of what that is before I explain it. Okay, if you were driving down the road on a day like today when it's nice and cold and, might be icy out, what substance would a salt truck want to use if they wanted to lower the freezing point of ice the most? Would it be sand, rock salt, or ice melt? Well, let's think about this. What's the difference? Well, we know that sand is covalent because it's two nonmetals. Rock salt has two things in it. It's got Na plus and a Cl minus. So it will dissociate into two ions when it comes in contact with water, when it dissolves in water. And ice melt, calcium chloride, will break up into calcium 2 plus and chlorine minus, but two of them. So it breaks up into three pieces. So the Van Hoff factor is talking about the number of particles produced per molecule. So for sand, a covalent compound, I would be 1, because covalent compounds don't dissolve or dissociate in water. Ionic compounds like NaCl and calcium chloride both will dissolve, they will dissociate, so you have to figure out how many ions are present in solution. So like we just said, for sand, or any covalent compound, I value will be 1. For an ionic compound like sodium chloride, the I value would be 2 because it breaks into 2 ions. And for calcium chloride, CaCl2, it would break into 3 ions. So that's how you figure out what the Van Hoff factor is. So let's try a calculation here. Remember that our equation is delta TF equals negative Kb times M times I. We are given the Kf value here for water, and what we're trying to figure out is the new freezing point of water. Now, this equation is just going to tell us how much the freezing point changes. So at the end, once we find that, we'll have to subtract it from what the normal freezing point for water is. Do you know what that is? Yeah, the normal freezing point for water is 0 degrees Celsius for H2O. We won't always be using water, but I will always tell you what the freezing point of that liquid is. Okay, so we know Kb. We don't know the other two. Let's see, I. How do we figure out I? That's probably a little bit easier. Well, let's look at what our solute is. Our solute here is glucose, and its structure is C6H12O6. That's covalent, so our I value here is just going to be 1. Now, let's look at the molality. This is going to require some calculation. Remember, molality is moles of solute, so in this case glucose, divided by kilograms of solvent. So in a denominator, we're definitely going to put 2.5 kilograms. It was nice of me to provide you with the kilograms, so no conversion needed there. But we will need to convert our grams of glucose into moles. So 168 grams of C6H12O6. Convert that into moles using the molar mass. 1 mole of glucose weighs 180 grams. So when you divide that, you get 0.93 moles of glucose. So that would go in our numerator. So our molality here would be 0.373 molal. Okay, so into our delta TF equation, we will plug in negative 1.86 times molality, which was 0.93. Oops, I used the wrong, oh no, that's right. That's the wrong number. 0.373 molal times I, which is 1, because it's a covalent compound, glucose. Multiply those together, and you see that the freezing point will be depressed by 0.694 degrees Celsius. That's not a whole lot, so glucose isn't very effective at lowering the freezing point of water. Now, remember we said this is just how much it changes. The normal freezing point for water is 0 degrees Celsius, so if it goes down by 0.694 degrees Celsius, what will it be at? Well, 0 minus 0.694 would be negative 0.694 degrees Celsius. That would be the answer to number 1. Okay, next up, boiling point elevation. This is the opposite of freezing point depression, but it's the same kind of idea. The boiling point is the temperature where something boils, and that happens when the vapor pressure, so the pressure of the solvent above the liquid, equals the atmospheric pressure. Now, the atmospheric pressure isn't going to change when you make a solution, but the vapor pressure does. And the result is that the boiling point is elevated. Why? Well, we know that the vapor pressure is lowered when you add the solute. So when the vapor pressure is lower, you're going to need more kinetic energy to make more vapor pressure. You're going to have to heat it up, get to a higher temperature to get the same vapor pressure that you had before to make it match the atmospheric pressure that's remained constant. And we do this a lot when we cook. You may add salt to water when you boil it for making macaroni and cheese or spaghetti and meatballs. Well, why do you do that? Well, the idea is that the water will get to a higher temperature when there's solute in there because the boiling point is elevated. So it will cook your spaghetti faster. Remember that when you get to the boiling point, the temperature isn't going to change. The temperature is going to stay constant as all that liquid water evaporates. So if there's no solute in there, then it would just boil at 100. Theoretically, by adding some salt, the temperature should get up to like 101, 102, 103. It should get a little hotter. And so the water will be hotter as it boils. making your spaghetti cook faster. Actually, though, we're going to do a calculation here in just a minute that shows you that it's going to take a lot of salt to make a big difference in that temperature. So really, it's just for seasoning. The equation for boiling point elevation is very similar to the one for freezing point freezing point depression, except that we're going to find the change in the boiling temperature by using the Kb value, the boiling point constant, and notice that it will be positive because we're going to elevate the boiling point. Molality, the Van Hoff factor are all the same. Okay, here's our calculation. Let's say we dumped 32.5 grams of sodium chloride, that's a lot of salt, into 950 milliliters of water. That's just 1 quart of water, about what you'd use to make a pound of pasta. If the Kb for water is 0.512, and well, we know that water normally boils, the normal boiling point for water is 100 degrees Celsius. Let's find the new boiling point. Okay, so our equation was delta Tb equals Kb times molality times I. I like to start with the I value because that's generally pretty easy to figure out. The I value goes with your solute, which in this case was sodium chloride. Make sure you always write the formula, looking at the charges, crisscrossing the charges if necessary. In this case, we don't have to though. So sodium chloride would break up into Na plus and Cl minus. So our I value is going to be 2. And our Kb value we know is 0.512. Now we just need to find our molality to plug that in. Molality is moles of solute per kilogram of solution. Okay, so we're going to have to think about this for a minute. We've been given 950 milliliters of water, which is 950 grams, assuming that the density is 1 gram per milliliter. And in kilograms, that'd be 0.950 kilograms. And the moles, so on here we'll put 0.950, and then the moles are going to be 32.5 grams of NaCl times 1 mole of it over the molar mass in grams. And for sodium chloride, the molar mass is 58.5. So that would be 0.556 moles. Okay, so the molality, 0.556 divided by 0.95, turns out to be 0.585 molal. So we will plug our molality back into our boiling point elevation formula and then multiply that out, and I believe you should get 0.599 degrees Celsius. That means when we add a whole ton of salt, okay, not a ton, but a whole lot of salt to our water, the boiling point only goes up by about 1/6 of a degree. So our new boiling point, which we're trying to find, would be 100, our normal boiling point, plus how much it's elevated. So it would be about 100.6 degrees Celsius. And if you round it, maybe 101 degrees Celsius. So really you're not getting a whole lot of benefit, and you're probably going to give yourself high blood pressure by eating all that salt. Okay, why don't you try this one on your own? The difference here is that we are mixing it into a solvent of phenol. So our normal freezing point is not 100, not 0, and our Kf value is a little bit different. Try this one on your own, then tune back in to see the answers. Okay, here are the answers. One thing you may not have caught is that magnesium bromide is MgBr2. Did you crisscross? So when you're finding the molality, first thing you want to do is convert it into moles by using the molar mass. Then you will divide the moles by the kilograms, and you'll end up with a solution that's 0.365 molality. The I value will be 3 because you'll have a magnesium and 2 bromines. Oh, there's the bell. So we'll wrap this up. The change in freezing point temperature will be Kf times the molality times the I, which is 3. So the freezing point will go down by 8.1 degrees Celsius. The normal freezing point is 40.9. If it goes down by 8 degrees, that's a pretty hefty change. It'll go down to 32.8 degrees Celsius. Okay, folks, happy freezing.